Hey everyone, in this video we'll take a look at the math behind backpropagation. In our previous video we discussed the training of a neural network, and in that video we saw that backpropagation is the algorithm we use to compute the gradients of the loss function with respect to our weights and biases. This helps us know how much we need to adjust our learnable parameters in order to reduce the loss and improve the accuracy of our network. To calculate these gradients, backpropagation uses the chain rule of calculus. This rule helps us calculate the derivatives of composite functions. A composite function is a function that takes to its input another function. It's basically one function inside of another. Let's say we have a function f which takes to its input another function g. The chain rule says that to compute the derivatives of f with respect to x, we first take the derivative of the external function f with respect to g of x and multiply it by the derivative of g with respect to x. Now that we understand how the chain rule works, we'll look at its application in computing the gradients of our neural network's loss function with respect to each weight in the network. But before we get to that, I'd like to go through the notation so that everything is clear and unambiguous throughout the video. We'll start with L, which describes the number of layers in our network. We'll use small l to index these layers. For this particular model, L is equal to 4. We will also use L is equal to big L to describe the output layer, and L minus 1 to describe the layer just before the output layer. To describe the nodes within a given layer L, we'll index them using j, and our j will go from 0 to n minus 1, with n being the number of nodes in the layer. To describe the nodes in the previous layer L minus 1, we'll use k as our index, which also goes from 0 to n minus 1. We also have the weights within the connections in our network. This will be denoted as W with the superscript L and two subscripts j and k. This gives us the weight of the connection between node k in layer L minus 1 and node j in layer L. For example, this particular weight between node 1 in layer 2 and node 2 in layer 3 will be denoted as W with the superscript 3 and two subscripts 2 and 1. To describe all the weights that go into a single node j in layer L from the previous layer, we write W sub j with the superscript L. This will give us a vector of all the weights from layer L minus 1 going into node j. In our example, we have all the weights going into node 2 of layer 3 from layer 2. Each layer of our network has an activation function. This will be denoted g with the superscript L, meaning g superscript 3 will be referring to the activation function used in layer 3. To describe the output of this function on a node, we will use a with the superscript L and subscript j. This will be the activation function's output of node j in layer L. For our activation function to compute the activation for a node, it takes inputs from nodes in the previous layer. We will describe the input that goes into a node as I with a superscript L and a subscript j. This will be referring to the input to node j in layer L. We know that the input to a node is computed by taking the activation outputs of all the nodes in the previous layer and multiplying them by the weights that connect them to our node. So we may describe the input to node j in layer L as the summation of the products between all the activation functions from nodes in layer L minus 1 and the weights in the connections that connect them to node j. This helps us view the input as a function of the weights in the connection. The activation input of a node is by definition the output of the activation function used on that node. This means that we can express the activation output of node j in layer L as equal to g of layer L with the input I of node j in layer L. We also want to describe the desired output for our model for a single training example. Recall that we said the model displays predictions in the output layer. To describe the desired output for node j in the output layer, we will use y with the subscript j. For example, if the desired output for node 1 in the output layer is 1, for a given training example, we'll say y sub 1 is equal to 1. We'll use delta to describe the loss function for our model, given a single training example. For this video specifically, we'll use the sum of squared errors for our loss function. This is a simple function that takes the difference between the activation outputs of the nodes in the output layer and the desired values y sub j for all the nodes in the output layer. For each node, this difference is squared and then we sum up all these squares. Let's think about a single node j in the output layer. Since the loss for our entire network has been defined as the summation of the loss calculated at all nodes in the output layer, we can think of the loss at just node j as delta sub j, and it is equal to the activation function of node j in layer L minus the desired value for the node squared. This way we can think of the loss at node j as a function of the activation output of that node. And since we have already seen that the activation output of a node can be expressed as the activation function of that layer applied to the node's input, we can think of the activation output as a function of the input that goes into that node. We also know that the input to our node is computed as the summation of the products of the previous layer's activation outputs and the weight of the connections that connect them to the node. We can therefore think of this input as a function of our weights. Putting all these functions together, we can think of the loss on a node j as a composite function, delta sub j, that takes to its input the activation output of j, which is also a composite function that also takes the input to node j, which is a function of all the weights of the previous layer that go into node j. And since the loss of our network can be seen as a summation of the loss in all the output layer nodes, we can describe delta as a summation of j from 0 to n minus 1 of delta sub j. Now we said that backpropagation helps with calculating the derivatives of the loss function with respect to our learnable parameters. And we know that the way these learnable parameters are updated is starting from the output layer moving backwards. To see how this is done, we'll focus on a single weight. For our example, we'll use the weight that connects node 2 in layer L-1 to node 1 in layer L. Recall that our loss is a composite function. Now using the chain rule, the derivative of the loss function with respect to the weight that connects node 2 in layer L-1 to node 1 in layer L will be equal to the derivative of the loss with respect to the activation output of node 1 in layer L multiplied by the derivative of the activation output of this node with respect to the input of node 1 in layer L multiplied by the derivative of this input with respect to our weight. Now to compute this derivative, we'll take a look at each term of this equation, starting with the derivative of the loss with respect to the output of node 1 in layer L. We know that the loss for our network is equal to the summation of j from 0 to n minus 1 of the activation output of node j in the layers minus the desired output of node j squared. Now expanding this summation for our network, we would get the activation output of node 0 in layer 4 minus the desired output of that node squared plus the activation output on node 1 minus the desired value squared. Now to get the derivative of the loss with respect to the activation output of node 1, we will use the sum rule of calculus on our loss function and get the sum of two derivatives. The first derivative will go to 0 because that function does not have a sub 1 in it, and we are left with the result from the second derivative. Moving on to the second term on our equation, we have the derivative of our activation function with respect to the input to our node. We know that the activation output of node 1 in layer L is equal to the output of the activation function in layer L, with the input of node 1 in layer L passed to it. This means that the derivative of our activation output with respect to the input will simply be g prime with the output passed to it, meaning it will be the derivative of whichever activation function we'll be using for our layer. Now for the final term, we'll have the derivative of the input into node 1 in layer L with respect to our weight. We know that the input into a node in layer L can be expressed as the summation of the weights in the connections between all the nodes in layer L-1 multiplied by the activation outputs of these nodes. Now just like our first term, we'll expand this summation, and for our example we'll get this summation. We will then apply the sum rule to get the derivative of our input with respect to the weight. Now if we visually inspect these derivatives, we'll notice that only one term has our weight in it, meaning the rest of these terms will go to 0 while we are left with a sub 2 as our derivative. Putting all three parts together, we get this value. This will be the derivative of our loss function with respect to our weight given one training sample. Since we said that during training several samples will be passed through our network, then we may want to calculate the average derivative of the loss function with respect to our weight. We'll call this delta, and it will be equal to 1 over n, with n being the number of training samples, multiplied by the summation of the derivative of the loss with each training sample with respect to this weight. After calculating the derivatives for all the weights connected to our output layer nodes, backpropagation moves backwards through our network to calculate the weights of the connections going into layer L-1. Generally speaking, these derivatives are calculated the same way as the derivatives for our output layer connections. However, the first term will be calculated differently for non-output layer connections. We'll look at the math for how backpropagation moves backwards through the network in our next video. So if you want to see that video, subscribe to the channel and like this video if you found it helpful. Thank you guys for watching, and I'll see you in the next one.